Hello again, and in this video we are going to look at the 6 crystal systems. This is a very important part of our study of minerals because if you look up a mineral in either a textbook or a field guide, you're almost certainly going to see two things right away: the chemical composition, the formula, but then also the crystal system. So if you look up quartz, you'll see it's SiO2, and then you'll see that it is hexagonal. So a hexagonal is related to this idea of a crystal system. It's one of 6 possibilities. And so we're going to look at those 6. Now, before we do, we need a little bit of terminology. When we talk about the axes of a set of crystals, we can write them as 3 lines, one going front to back, we'll call it A, another left to right, B, and then top to bottom, the vertical is C. This is by convention. We always write the A, B, and C axes to represent crystal symmetry in this way. So when we talk about a C axis in every diagram, when we draw a picture of a mineral, that C axis would be vertical, for example. And then there are the relationships. So in this case, let's take the case that A is not equal to B in length, and B is not equal to C, so none are equal. And let's say we have angles where none are at 90 degrees. Now, to talk about the angles, we'll use the letter absent notation. So if we want to discuss this angle here between A and C, we'll call it beta using the second letter of the Greek alphabet. So A angle C will be referred to as beta. And let's just say in this case that it is not equal to 90 degrees. And then C angle B. The missing letter there is A. So we'll use the first letter of the Greek alphabet, alpha. And let's say, just for fun, that this is also not equal to 90 degrees. And then we have this third angle, and the third letter of the Greek alphabet is gamma. Let's say it's not equal to 90 degrees, and this is the angle of B and A. C being the missing letter in that notation, so we'll use that third letter in the Greek alphabet, gamma. So this is the angle gamma, and then this is the angle beta here, and that's the angle alpha there. So if we have all of these characteristics here, this gives us the first of the 6 that we will examine. This is the case of a crystal that would fall into the triclinic system. And what we'll do is we'll gradually increase the symmetry as we go. So how about the case for C, B, and A all being unequal in length? So A does not equal B does not equal C, and here again we are referring to length. But let's say that C and B are perpendicular. So that is a right angle. We could draw a little square there. And let's say that B and A angle B, are also at 90 degrees. But then alpha, this angle here, not alpha, this, if we're looking at the angle between C and A, the missing notation would be B, so we'll call it beta. And so in this case, beta does not equal 90 degrees. So in that case, we would have monoclinic. And you could break this up into its Greek roots. Mono means one, clinic, that's from cline or incline. So there is a single axis, in this case the A axis, that is inclined. And that is the only fellow that's inclined here. All the B and C are perpendicular to one another, and so is A and B. And then none of them are equal in length. What if we were to straighten it out a bit? So we'll still take the case that A, B, and C are unequal. So again, A does not equal B, does not equal C. But let's say all angles of alpha, beta, and gamma are perpendicular. So these are all right angles to one another. Well, in that case, we would have the group, not that one, yes, that one, orthorhombic. And the pen is acting a little bit slow, but we'll get this done. So there we go. We have an orthorhombic crystal. So this is the case where all of the axes are unequal, but all of the axes are perpendicular to one another. So now we'll add a little bit more symmetry. So what we will do is we'll take the case that we have a distinct C axis, but now we'll let the A and B axes be equal. But if they are equal, there's no need to call them A and B. We could just call them A1 and A2 because they're the same. They would be indistinguishable. If we had atoms scattered around these kinds of axes, you wouldn't be able to tell whether you were looking down the A1 or the A2. So there's no point in calling them A and B. And so we don't call them B, we'll call them A1 and A2. So here, A1 is equal to A2, but these are not equal to C, and all of them are perpendicular. And that gives us the case of the tetragonal system. Right? Then we can have the case where all are perpendicular and all are the same. So we'll let C be the same as A, but in that case we don't have to really call it C. So A1 equals A2 equals A3. That's why we give them all the same letter. All are perpendicular to one another. And in this case, we would have a cubic system. We would get a very nice cube. So we've covered everything except the one we started off with as an example for quartz. What about the hexagonal system? The hexagonal system would be a case where we have a C-axis, could be long or short, and then we have three axes here, and those axes are situated, so we'll call them A1, A2, and A3. And these are all at 120 degrees from one another. So the angle between A1 and A2, that's 120 degrees. And then the angles between A3 and A2 would be 120. They would all be 120. So in this case, C does not equal A, any of the A1, A2, or A3, but we have 120 degree angles for our A1, A2, A3. And then C would also be perpendicular to the A axes. And this is our hexagonal system. So those are our 6 systems. And these are ways, very common ways in which minerals are classified.